Hello and welcome to this session on network automation with Ansible and Napalm. I'm Patricio Martello.
Hi everyone, I'm Romain Bastard.
I'll start with a brief introduction to Napalm, the network automation and programmability abstraction layer with multi-vendor support. It is a bit of a mouthful, but it is a very powerful tool to help automate networks in a multi-vendor environment.
I will continue with a simple demo in which I will use Python and Napalm to take a network configuration backup.
After that, we move on to Ansible. I will explain how to take this to the next level by creating abstract network models that allow us to automate the deployment of an entire network and the services running on top of it in a multi-vendor environment. That is, running network infrastructure as code.
And I will demonstrate how to do that. We will automate the entire deployment of a multi-vendor network from scratch, including OSPF, BGP, and VXLAN services running on top. If you want to do the lab on your own, I have created a Docker container which is pre-built with all required software and samples used in the demo.
So let's begin. Okay, so with that introduction, let's talk about Napalm first. So what is Napalm? It is a Python library that abstracts network functions across devices from different vendors. You may be asking which functions it abstracts. We will get to that in a minute. It's extremely useful when we need to automate tasks in a large mixed vendor environment, or maybe an environment that is not so huge but that changes very often. Each vendor provides a driver which Napalm uses to talk to that vendor's hardware. The driver will communicate with the hardware using the vendor's specific interface and methods. But those differences between vendors are abstracted, and that's the point. There's a couple dozen drivers from different vendors, including routers, switches, firewalls, load balancers, etc. And this abstraction allows the network engineer, or shall we say network programmer, to write code implementing automation functions and use exactly the same code no matter what the vendor's operating system is, because Napalm will just simply use the right driver according to the required OS, and those differences, let's say, between AOS, EOS, iOS, Junos, etc. are abstracted. For example, both the AOS and iOS Napalm drivers use CLI commands over an SSH connection, whereas the EOS driver uses JSON objects over an API, and even the Junos driver uses XML objects over a netconf connection. And even though both AOS and iOS use CLI over SSH, of course, the AOS CLI and the iOS CLI are different. But all these differences are abstracted, and the network programmer can create a single piece of code to perform actions over a diverse set of equipment without worrying about the different interfaces such as SSH, API, or netconf, whether the devices use CLI, JSON, or XML, or even being aware of the CLI differences between, let's say, iOS and AOS. All that will be abstracted, except for the fact that on AOS and iOS we need to enable SSH access, and on EOS we need to enable API access, and in Junos we need to enable netconf access. Let's now talk about Napalm methods. Methods are classified in 4 different groups. There's getters, there's setters, there's others, and there's file manipulation. Get methods extract information from network devices very much like a show command. But unlike a show command, get methods return structured data in a dictionary format, which is much easier to work with than parsing CLI output. Not to mention, of course, that the structure is the same regardless of the OS version. Some examples are get facts, config, interfaces, ARP, BGP neighbors, etc. There is a much smaller group, which is the setters. Through these methods, we can push configuration to the device. We can configure the host name, NTP peers, we can configure SAA probes, etc., but not a whole lot more than that. Then there's the others group for loading a template or doing a ping or a trace route. And lastly, there's a file manipulation group. With these methods, we can, for example, replace or merge a configuration file. There's support for loading a candidate file, comparing it to the running config, and committing or discarding the changes. As you can see, since the setters are quite limited for performing configurations, most configuration is done by file manipulation. What that means is that in most cases, we need to either create a new config file and apply it, or we need to create a delta configuration file and apply the changes. In this manner, we can treat network device configuration similar to application configuration. We can have different repositories with different releases of the network configuration, and we can load, compare, commit, discard, or roll back those releases. Here, when I say releases, I'm not referring to operating system releases. I am referring to configuration releases to the network state. The bottom line is, in this manner, we can manage network infrastructure as code. In the example that we see on the slide, we have a base folder with config files for each device, and these config files include the bare minimum such that we can connect and manage the device. For example, the management IP address, authentication settings, SSH or API interface, etc., but not much more than that. Then we could have a production folder with the production release, a backup folder, and then we could have other folders with other releases that may still be in development or under testing. And of course, before applying a new release, we need to go through a change management process and test, validate the configuration in a test environment, and finally approve it or not before we apply it, because otherwise we could be automating the deployment of mistakes at scale. Now it's time for the first demo, in which Romain will cover a few things. One is how to install a pre-configured Docker container which comes with Python, pip, Napalm, Ansible, etc. Second, a sample Python code that will leverage the Napalm driver to take backups from 5 network devices, some of which are ALE AOS, whereas others are Arista EOS and others are Cisco IOS. By the way, if you would rather install all this software yourself, please refer to the installation instructions document within the Spacewalkers page. It also provides instructions on how to clone into a GitHub repository, which includes all the code for the different demos shown in this session. So, over to Romain.
So in this demo, we're going to see how to install a dedicated container to benefit from the full environment for Ansible and Napalm. So as you can see, I'm using a Linux machine that is located on a management network. So it will be the same network for the nodes, the future nodes. I'm using the Docker version 20.10.10. So now we can just run this command to install the container that is hosted on Docker Hub. So as you can see, the container is called Enterprise/Ansible, and we run the command bin bash as an interpreter to communicate with the machine. So we can run this command and it will download the container from Docker Hub. So we can see that the container has been successfully downloaded and it's actually running. So every file that we will use are located on the home work directory. So as you can see, we have the network folder that we'll use later, the service one also. Then we have the backup folder that we will use in this demo. So in this one, you can see that we have 2 files, the backup script written in Python. So this script will automate the backup of a network for the switch or the router. Then we have also the inventory.csv file that acts as a database. So let's have a look on the two files. So as you can see, in the backup script, we import the Napalm library. Then we open the inventory.csv and we load the driver according to the OS. We load the host, the username and the password. Then we open the connection and we save the config file. So you know, in the inventory you have 4 columns, one for the OS, one for the host, one for the username and another one for the password. So to test the script, we are going to run it. We can see that we have as many files as we have nodes in the inventory.csv file. So to test if the configuration, if the script works properly, we are going to open 2 of them. For example, leaf1. We can see that the configuration file is okay. And it's also the same for the Omni switch. So the backup script works well, so we can proceed to the next part of the demo.
Thanks, Romain. Let's now move on to Ansible. Personally, I think that what we just saw is amazing enough. We saw how the exact same code can perform actions on devices from 3 different vendors without any change to the code. But with Ansible, we can take it to an entirely new level. As amazing as using the same code on multiple devices running different operating systems might be, there is still something which is missing. We could build other scripts to do more than just taking a backup. We could push configuration changes to the devices, but as I was saying earlier, most configuration changes are done through file manipulation. So, we would still need to create the configuration files or delta configuration files for each device in the inventory file. And when doing so, we would need to use the right CLI for the right operating system because Napalm in itself does not abstract the CLI. So, if we were to roll out a new configuration release, it's the network engineer that would need to create one configuration file for each device in the inventory using the right CLI according to its OS. Of course, this is a tedious job. It's time-consuming and it's prone to errors. Ideally, we should be able to automate and abstract the file creation process too. And that's where Ansible comes in. Before we can start automating with Ansible, we need an abstract and vendor-neutral representation of the network. That is a network model. If we look at this network diagram, which is what Romain will use in his next demo, it's a spine and leaf topology using OSPF and BGP routing with route reflectors. This diagram is already an abstraction and it is vendor neutral. It only contains generic things such as IP addresses, OSPF or BGP parameters and so on, but nothing here is specific to any vendor except for the declaration of the operating system. Of course, a diagram is not a friendly format for a script to take as input. So we will take this diagram and we will represent it as a YAML model, that is a text file and a host file, also a text file which contains the OS and logon details for each device. You will see the network model in the demo. Similarly, we can also create an abstract service model for services such as MPLS, SPB, or, as we see in the example, VXLAN services. Services, especially in a service provider environment, require much more frequent changes than the network infrastructure itself. So it makes sense to keep services separate from underlying network infrastructure and only generate delta configurations for those services. In the same manner, we can create a service model template and we can change services as required without upsetting the underlying network configuration. So what is Ansible? Ansible is software to automate provisioning and configuration across multiple hosts, such as Linux hosts. Network devices are just a special type of host. There's a whole lot more that could be said about Ansible, but for the purpose of this session, I will stop here. How do we go from an abstract model to an actual configuration file that we can deploy on a network device? We can do it in 3 steps. In the first step, we take the abstract network model and translate that to a node model. This is done using Jinja templates. This may be more clear when we see the demo, but the difference between the network and the node model is that the network model has things grouped by function, whereas the node model has things grouped by node. Going from network to node model is an intermediate step that helps with the next step. It would be much more difficult to go from network model directly to configuration files in one go. Jinja templates take the network model and turn it into a node model using variables, conditional and iterative statements, etc., like most programming languages. But Jinja templates are quite simple and effective for handling this type of text files, which are configuration files. We now have the node model, which is essentially the same thing as the network model, just with separate sections for each network node. It's just there to make the next step easier. So in the next step, we take the node model and we use Jinja templates, one for each operating system, which are like translation engines that translate the abstract node model into configuration files using the specific CLI and syntax for each network node according to its OS. So the example that Romain will show uses both AOS and EOS. So there's 2 translation engines, one for OmniSwitch AOS and another one for Arista EOS. Finally, these config files are pushed to the devices using Napalm. We can think of these 3 steps as 3 acts in a play. In Ansible, the play is called a playbook. In our demo, the playbook is called network deploy. And there's 3 distinct plays: creating the per node model, generating the configuration files, and lastly, pushing those configuration files to the network nodes. Similarly, we can have the same structure for the services running on top of the physical infrastructure. We start with a service model. We use one Jinja template to turn that into a per node service model, and then a set of Jinja templates to convert the per node service models to the various CLIs and syntaxes for the different network nodes. In our example, we use 2, one for AOS and another one for EOS. Finally, we push those config files. So we put all these on an Ansible playbook again that we call service deploy, and it has 3 distinct parts. The first one is to create the per node service model. The second one is generating the configuration files, and the third one is pushing those configuration files to the network nodes. It is now time for the second demo, in which Romain will show how to use Ansible playbooks to deploy the network infrastructure, that is, the 5 nodes in a span and leaf architecture using OSPF and BGP with a mix of AOS and EOS devices. So, over to Romain.
So we are back in our container, and before to push any configuration, we're going to do a little walkthrough about the various files that are important to understand. So the first one is the network model.yaml. As you can see, we have a nodes section that contains every node's information of the network. So the name, the management IP address, and the future router ID. Then we have a section for the links. So it represents every connection between each node. we have the name, the port associated, the IP address and the VLAN, and also the cost. Then we have the information related to the routing protocol. So the first one for BGP, we can see that we have the two spines are going to act as a router reflector, and the three other leaves are going to act as clients, and it will be only set for IPv4. For the OSPF section, we have set an area as 0 and the network as a point-to-point connection. Then I'm going to show you the playbook. So as you can see, the playbook is separated by three major sections. The first one will consist to generate a per node configuration model. So it will retrieve any data for each node and set an individual configuration. So the output will be the node model.yaml. In the second play, we're going to take as input this node.yaml file, and we're going to translate this YAML configuration to a final configuration for the end node, thanks to the translation with the Jinja template. And last, we have the third play that will consist to push the configuration to the final node. So we can see that we invoke the Napalm install config module and the various parameters to be connected to the final node. So the host, the user, and the password. So we can deploy the playbook. But before, we are going to take a look on switches to see that there is no configuration yet. So first, we can try to connect to leaf 1, for example. So as you can see, there is no configuration yet except the management IP address and the API. So basically to be connected through SSH. So we can have a look on an anomaly switch. For example, leaf 3. So as you can see, it's the same thing. We only configured the authentication through SSH and the management IP interface. So that's all. We can push the playbook. So as you can see in the load configuration to node, we can see that every node have a new configuration. So to verify if the playbook works properly, we're going to try to connect to leaf 1, for example. So we can see that there is some change. Every information has been successfully added. We can see that we have interface set correctly. The BGP section is also filled correctly, and the OSPF part also. So to verify, we're going to try to connect to another switch. So it's the same thing. OSPF and BGP seems to be well configured. So we're going to try to show the routes. So we can see that we have all the router ID in the destination address table. We're going to try to ping one of them. So as you can see, the connectivity works properly, so we can move on to the next part.
Thanks, Roman. And what we just saw is that working in this fashion, we can have a single source of truth abstract level model, which does not depend on the operating system. Thanks to Jinja templates, Ansible, and Napalm, you can turn that abstract model into OS-specific configuration files that you can push to the device. In the next demo, we will see how to work with a services template and playbook to add overlay VXLAN services on top of the underlay that we have just deployed. So, over to you, Roman, again.
So to continue this demo, we're going to add a new VXLAN services on top on a running network infrastructure. So in this file, it's the same thing as we previously saw. Typically, it's an abstract representation of the service we want to implement. So we have the node list of every node that are present on the network. We have also a service list with common parameters, typically the name of the service, the VNID, and the VLAN. And then we have a field called sites that host every information of the member of the future VXLAN connection. So typically it will be between leaf 1 and leaf 3. And also we can see that we have the interface associated to this service we want to implement. So all the traffic, the VXLAN traffic will pass through this specific interface. Then we have the playbook we want to push. So it's separated by 3 major plays. The first one is the same as we already saw. Is to create a node model file to create an individual configuration for each node. Then we have the second play, which consists to translate this YAML file into a config file for the destination of the node. And the third play will be to push the configuration to the final node. So before deploying any playbook, we will connect to a laptop that is located behind the leaf 3, and to see there is no connectivity yet. So we are now behind the leaf 3 laptop, and we're going to try by a ping to test the connectivity to the desktop located behind the leaf 1. And as you can see, there is no reachability yet, so we're going to move on the container to deploy the playbook and test again this reachability. So we are back in the container, and the last thing that we need to do is just to run the playbook. So as you can see, leaf 1 and leaf 3 are in yellow state. That means that the configuration has changed. So to verify that the connectivity is successfully done, we're going to move on the desktop located behind the leaf 3 and test again the connectivity. So we are back in the laptop, and we are going to try again a ping. So as you can see, the book successfully worked. We can see that we have a reply from the end node and the end laptop, and we can move on to our container to see how to add a new service. So we are back in the service model.yaml file, and the purpose of the manipulation will be to add another service. So thanks to the flexibility of Ansible and Napalm, we have two choices. Either add a new member of an existing VXLAN configuration, or we can also create another VXLAN service by adding these following lines. So typically, we create another name, for example, customer2, with a different VNID and a different VLAN, and we specify the leaf that will be concerned by this connection. So it will be between leaf 1 and leaf 2 on this following interface. We just need to save the configuration. So as you can see, we have some change between leaf 1 and leaf 2, and the configuration has been successfully uploaded to the final node. So that's the end of this demo.
And what we just saw is that working in this fashion, we can have a single source of truth abstract service model which does not depend on the operating system. Thanks to Jinja templates, Ansible, and Napalm, you can turn that abstract model into OS-specific configuration files that you can push to the network devices. It's good to keep underlay models and templates separate from overlay models and templates because the overlay, that is the services part, will likely change much more often than the underlay. The underlay is typically much more set and forget than the overlay. Changes to the underlay may require more thorough change control and maintenance windows, whereas changes to the overlay could happen on the fly. So I hope this gives you a good idea of how we can combine Napalm, Ansible, and work with Jinja templates to completely automate the deployment, the configuration, and the operation of an entire multi-vendor network and the services running on top of it. There is definitely a lot more that we can do with that. We are only scratching the surface. For example, we could automate test and validation of the network and its services. We could check that the IP addresses are correct, that the interfaces are up, that the LLDP neighbors and the BGP connections are correct, and if not, we can build the appropriate steps into a workflow. Lastly, having this single source of truth for the network and its services helps with network consistency. It helps eliminate configuration drift and snowflakes, which in the end also helps with compliance.
This brings us to the end of this session. Let's wrap up with some key takeaways. Ansible and Napalm combined are two extremely powerful tools to automate repetitive tasks in a multi-vendor environment. We can run network infrastructure as if it were code.
What's more, by centralizing all network configuration changes, we can have a single source of truth to keep network configuration uniform, consistent, compliant, and free from human error.
And we can easily implement change control audit for compliance, and in case of configuration drift, we can quickly bring the network back to the compliant state.
And these are just some of the benefits. We hope you have enjoyed this session. I invite you to exchange with us in the Spacewalkers forum, and see you next time.
And I encourage you to try it on your own. Take care.